Hey there, how you doing? Welcome to the channel. So I do want to do a clock update. So our clock project we're working on here is going to be basically a clock and a calendar. So we have these two digits now. They're not counting seconds; they're actually testing that we're kind of reading the years, the minutes, all the stuff. But what I want to address here is that. Over to the right here, see that regulator at the end of that breadboard, and it's got basically the door stopper hooked up to it. What's happening is I was trying to figure out like why this is the 1.5 volt regulator. So it's a 317T adjustable regulator set to 1.5 volt output. Now, the input voltage coming in is at 12 volts from the DC wall wart. And so the problem is what I didn't really realize is how much power that thing is going to dissipate. Now, in the middle here, you see that, this is a regulator module, and this is, taking that 12 volts and stepping it up to 20 volts for basically like the grid and the anodes for the vacuum fluorescent displays, right? And then this one here is just a regular 7805. Just a fixed 5 volt regulator. So, it's 12 to 5 volts here. That's really simple, no resistors or anything. Now, I needed this regulator here for the 20 volts because it could have gone as high as 30 volts, but I decided to stick with 12 volts. Okay, so that's all good, but I needed a regulator for that because I have to step up the voltage. So you need one of those chips that basically will boost it. And then the 1.5 volts, I was just trying to use basically a 317T with the resistors set to 1.5. But it turns out that this thing was getting so hot, it literally burns your finger. And so like if I go over here and I even touch this part, it burns, right? It burns, it'll burn my finger. It's so hot. And so I'm trying to figure out like why it's so hot. And so that was definitely one of the things that, trying to figure out. So let me show you what I realized. And so that's kind of part of this project. I realized stuff. I'm going to kind of share it. So we go into, let's see, we're going into our power calculations in the spreadsheet. So we had all these basically, okay. Hello. Oh my goodness, why does it do this? Okay, so we have all these calculations here. Hello. Okay, and so it turns out, so let me go over here. It turns out that the power dissipated, and so calculate the power dissipated in 317 and 708. 7805 devices. It turns out that the power dissipated is equal to the voltage drop, which is the V in minus the V out times the load current IL. So the thing is, so now I went through each one of the regulator voltages. So we have the 20 volts, that's a regulator. So that's a boost regulator. So that's something totally different. Then we have the 5 volt. Now, since the input voltage is so high, we're dropping 7 volts. And so that 7 volts means that 7 volts times whatever the current is going to give you the power. So basically what I had to do is go do these calculations for each of my cases. So per tube regulator power dissipation, basically you have to figure out the voltage drop. So now here's where it gets, because this 1.5 volt had got 12 volts coming in, we're dropping a whole 10.5 volts. And so the problem is it's dissipating a whole watt. And this is for, this is, so basically, okay, so we're dropping 10.5 volts. Okay, so let's go figure out what the power that we're going to be dissipating is. So let me show that calculation up here. So here we have our power supply. So 20 volt, forget about that one. Go to the 1.5, go directly to that. So we have 1.5 volt out. We have a voltage drop of 10.5 volts because what I have up here is set DC in 12 volts. So I can do different calculations, but we're using 12 volts here. So the difference is 10.5. Now, what I did is I had the actual measured current, which is 90 milliamps, and I added some margin in this column G. So I have 110 milliamps here. Okay, or 0.110 amps. So the power dissipated is simply the load current 0.11 or 110 milliamps times 10 volts. Now, because it's got such a huge voltage drop, because I'm going to such a low voltage, you literally we're dissipating a whole watt. And this is for a single tube. So for a single tube, we are dissipating a whole watt. Now, if you notice on the screen there, you'll notice that it's actually dimming, and it's dimming because I bet that voltage is dropping again, and it's dropping because in spite of the fact that I put that piece on there to try to like do a heat sink, it's still probably thermal throttling at this point. Now the question is why, and the reason it's thermal throttling is because look, per tube, so for 2 tubes, I'm going to have 100, 10 times 2. So for each one, it's 1 watt. Why is it 1 watt, even though I only have, 0.11 amps being delivered? It's because of the voltage drop, because I have such a high 12-volt input and I'm going to such a low voltage. It's actually really inefficient, really inefficient. The voltage drop inside the regulator is just burning tons of power. So the thing is, I have to affect that. I have to take into account the effect of that. So now if I do it and I go down my calculations for 12 and I have power with margin was the calculation I had before, but now I'm adding power dissipated in the regulators. So what I'm doing is I'm adding in the power dissipated in the regulators for the 12 tubes, okay? And so for the 20-volt supply, that's a module. We don't have to worry about it, right? So it's the same power, 13.6 watts, 13.6. Here, power dissipated in the regulator is going to be 5.7 watts for the 5-volt. So that's also, even though that one's not burning my fingers right now, it potentially could be burning my fingers. That's a lot of power. And then here's the problem. The 1.5-volt supply, if you look here, because we have so many of them, I mean, this is the most current draw. It's 110. It's like so much more than everything else. Across 12 tubes, you can have 1.32 total amps of current that you need to supply. If you take that, and so that's almost 2 watts, but you factor in using, in this case, the linear regulator, you're going to be at 15 watts. So basically, we can't do this. This is so inefficient. I mean, we're going to need a regulator, a 1.3 LM317T for each one of these regulators. And look at this. It's throttling right now. Look at that. If I turn this, if I let it cool off for a second, and then come back. Okay. And So that's just not even in the realm. And so when I originally set up to do this project, I was like, hey, I'll just use these regulators. I'm familiar with these 7805s and stuff. And I'm like, oh, I'm familiar with the adjustable. And I really never thought about the power. And I really honestly didn't quite realize that the amount of the voltage drop that affected the power. So this 15 watts is just not even an option. No way. And so that's why I'm burning my fingers, because I'm dissipating about 1 watt per tube, and I've got 2 tubes running off that. So I'm basically dissipating 2 watts, and 2 watts will burn your finger. So that's what's going on. So now basically I got to get rid of this linear regulator. The 7805s, the 317, they're linear regulators, and they're just not very efficient at all. And since I have to drive 12 tubes with 110 milliamps per tube, it's like, forget it. It's just not going to work. So what I look up is I'm basically going to go with another type of module. So I'm looking at another module, and I'm going to do the calculations here at the planned wall wart, which is the 19.5 volt. And so what we're going to have VN 19.5, 1.5 volt. And there from the data sheet, I was getting about 73% efficiency. I'll call it 70% efficiency. So total current at 1.5 is our 1.32 amps. Okay. Power I need to deliver is basically just the 1.32 times 1.5. Okay, so that tells me how many watts I need to deliver to the actual tubes. And then power needed to input so basically, if something's 70% efficient, then I have to deliver 30% more power. So basically what I said is I say, okay, I want 1 plus 1 minus the efficiency. So what you're going to get here is 130% times your input power. I'm sorry, 130% times the power you actually need to deliver, which is 1.98 watts. And that gives us 2.5 watts. And then what we can do with the 2.5 watts is figure out how much power is dissipated in the module in that case. So we are able to subtract the power needed at the input, which is, so we're going to put 2.5 watts coming in. 1.9 watts is going to go out. That's accounting for the 70% efficiency. That means 30% of that is being dissipated, and that's going to add up to about 0.6 watts in the module. So that should be okay. That chip can handle the 0.6 watts, and that's for the entire thing. So I need one module, and I'm going to get heat sinks for these as well. But so that really highlights how inefficient these like old linear regulators are. And like when you're, and I really didn't expect it, quite frankly. I mean, I look at something, I'm like, oh, you need 110 milliamps. That's not very much. So I kind of really honestly surprised about that. So yeah, so live and learn. So I'm going to get another regulator. And once again, we have a boost regulator here, and I'm going to use basically for both of these now. I'm not going to waste the 280 milliwatts here for the 5 volt either. So I'm going to get rid of the 7805s, getting rid of the 317s, and I'm going to have one module for each. And that one module will provide enough current for both for the 5 volts. So altogether, I'll just have 3 regulator modules. I'll have 1 boosting voltage and 2 that are like buck or down converting voltages. And so that was actually going to save a bunch of power and actually simplify things a lot. So, and then I'm using modules because I don't really want to get into the design of that. You have to, you know, it's not hard. It's just, you just have to, the capacitors, you have to design with the chips, and you have to, you do need some coils and stuff like that is what they recommend. So that's it for the power on that. If I stop sharing and we go back to our tube, I don't know if you can see this, but this is dimming right now. And it's dimming because this thing over here is like literally still burning my finger. Even if I touch it there, it's rather amazing. So if I unplug it for a minute and we let it cool off for a minute, then we'll plug it back in and it should be brighter. Well, it doesn't look much brighter, but it actually is brighter. You can't really see it. Yeah, so live and learn. So that's it for this one. So yeah, the power supplies. So I'm going to go use modules for all the power supplies because those linear regulators are just not very efficient at all. It was kind of interesting because back in the 70s when they were actually designing, you know, big boards with this, you know, 7400 series logic back in the probably in the 70s, I think they were doing that. I mean, if you look at stuff like the original Apple computer and all that stuff, they were using probably 7400 series logic. You know, they had the integrated processors, but they had a lot of logic chips in there too. And so, yeah, definitely like very inefficient stuff. And basically the way these boost and buck regulators work is they basically are going to have, they basically have an oscillator in there, and you're basically going to do switching. You're going to, you know, if you took like in a simple way, like I'm more familiar with it like at like a charge pump. So you have a capacitor and like a charge pump inside a PLL. And basically if you want to go, you want to up the voltage, you go in one direction, you apply some voltage, which adds some current, which increases the charge on the capacitor a little bit. And then if you want to lower the voltage, and you would basically just connect for a short period of time a resistor to, you know, drain a little bit of charge. And then the voltage is produces the basically frequency of the oscillator is proportional to the voltage. So you basically can have control circuits that are just, you know, they're constantly switching. They're constantly going up, down, until they get to an equilibrium where it's equal numbers of up, down. And so these regulators are a similar type of thing. You can take a voltage supply, you know, whatever it is, 20 volts, and you just change the duty cycle. Like if you wanted 20 volts, you want 10 volts out, okay, 50% duty cycle, smooth it with a capacitor, boom, you're good, right? So that's the kind of like the idea behind it. And then if you're, that would do that. And then the other way you would do it for switching it up, I think you have to kind of just switch the direction of it. So basically, if you want to go from 10 volts to 20 volts, well, you apply 10 volts to your capacitor, then you apply 10 volts in the reverse direction, and you basically are able to like charge it up to a higher voltage, something like that. So that's what we have to do, have to go and use that stuff. All right, that's it for this update. Talk to you later. Bye.